So a function formally is a mathematical relationship that takes the elements of one set and uniquely associates them with the members of another set or maps them onto that set. For every item in the input set, the function will translate that item into exactly one output value. Often we use letters like F, G, or H to denote a function, and we might use the notation you see at the bottom of the slide here to say that the function f takes elements from set A and translates them into elements from set B. Formally, if we have a function f that maps the items of A onto the set B, we call that input set A the function's domain. So the domain is the range is the set of input values where the function is defined. The output set B is the function's range. And another way of thinking about it is that if you took every single item of set A and ran it through the function, the range would be all of the values that were produced as a result. So now let's consider a few example functions. Let's take the function f of x is equal to 1 over 5 plus x. And we're going to ask for what values of x is this entire term on the real numbers. Well, as you look at it, almost anything will work. Almost any number from the real numbers can be plugged in here and produce another member of the real numbers. There's only one exception. If you think about the case where x equals -5, well, if we plug that in, we get 1 over 5 minus 5, or 1 over 0, which is not a member of the real numbers. So in other words, the domain, the set of values that x can take on, is going to be the set of x's on the real numbers except the number -5. So just to review the set notation here, we have the numbers x that are a member of the set of reals. Notice we're using this double script R to denote the real numbers. You use this backslash to denote with the exception or leaving out the set, and in this case the set is the single value -5. So now let's consider the range of this function f of x. We're going to ask, given all of these different values of x for the domain, what values can f of x take on? And so basically we want to just sort of consider the full range of x's. If we think about x being extremely large, that would be 1 over an extremely large number, which would be just barely to the right side of 0. Similarly, if we had an extremely negative number here, so -500 million, for example, that the whole term f of x would be very, very close to 0 just on the left-hand side. Notice that there is no possible way that we can make this expression equal to 0. Similarly, if we think about what would happen as we approach this left out number. So as we get closer and closer from either side to -5, we can imagine, for example, 1 over 5 plus -4.9999999999. And notice that what happens there is that you approach, although you do not reach 1 over 0, which means that you are approaching positive infinity. Similarly, coming from the other direction, we could think about, what about -5.000000000001? Well, again, what's going to happen is you'll get very, very close to positive infinity without actually reaching it. So as we think about all of those possibilities, basically what we've seen is that the range of f of x is going to be the values of f of x, again, on the real line, with the exception of the number 0. Notice that I could just as easily have written the range of f of x in interval notation. I could have said -∞, comma 0 but make it an open set so that we're not including the number 0, and taking the union of that interval with the number 0 to positive infinity so that we are getting the full set of reals with the exception of 0. So now let's consider another function. Let's say the function h of m is the square root of 2m minus 1. And so we'll start off by asking about the domain of the function. To see the domain, we need to ask for what values is this term, square root of 2m minus 1, a part of the real line. And we recognize that for that to be true, we need this term on the inside of the square root to be 0 or positive. In other words, this function is only going to be defined where the term 2m minus 1 is greater than or equal to 0. So to see the valid values of m, we can solve this. For m, we get that m must be greater than or equal to 1/2. So in other words, the domain, and we'll write it this time in interval notation, the domain of this function would be the closed set positive 1/2 to positive infinity. To think about the range, now we need to think about what values can the term square root of 2m minus 1 take on. And if you think about a square root, the square root itself is valid, or sorry, produces values that are 0 or greater than 0. And so since there's nothing else going on in this function, we can realize that the range of the function is going to be the full set of values of h of m on the interval 0 to positive infinity. I think it's instructive to consider another function, g of m, which is very similar to h of m. It's 5 plus h of m, 5 plus the square root of 2m minus 1. If we think about the domain, we're still asking for what values of m is this term 5 plus the square root of 2m minus 1 valid. And the domain is basically the same. We don't have any problem. Adding this 5 doesn't change anything. It's still the set of m's that are greater than or equal to positive 1/2. The range, on the other hand, has changed. So before we saw that the square root is going to produce positive or 0 numbers, but then we add 5 to that, which produces a range. Instead of going from 0 to positive infinity, now the function g of m goes from positive 5 to positive infinity. For our final example, let's consider this function z of t. And I want you to notice that we've combined the two problems we had with our last two examples. We have both something in the denominator that we need to make sure is not equal to 0, and we have a term in a square root, which we need to make sure is non-negative. It doesn't really matter which order you go with, so I'll just start off by recognizing that the denominator here cannot be negative. In other words, we need for t to never be equal to positive 8. So that's one limitation on the domain for this function. We need to force the denominator to not be 0. And now we're going to consider the full expression 1 over t minus 8 and ask, when is 1 over t minus 8 greater than or equal to 0? Hopefully you can see that this term 1 over t plus t minus 8 will be non-negative when t minus 8 is non-negative, and so that is simply where t is greater than or equal to 8. Now I want you to notice something. If we just had the square root, we would include the value of 8, But in this case, because we have the 8 in the denominator, we need to exclude 8. So the domain of this function, z of t, is going to be the values of t, where t is on the open interval 8 to positive infinity, not including the value of 8 itself. The range on this function is going to be very similar to what we saw with the other square root function. Specifically, we know that this can only ever be positive. But remember, with the other square root function, we included the value 0. But notice that this term, 1 over t minus 8, never takes on the value 0. So if you think about the range of that earlier function we saw that had a denominator of this form, it could never take on the value 0. So the range of this function is going to be the values of z of t can take on anything between 0 and positive infinity, not including the number 0, because 1 over t minus 8 can never be equal to 0. When you're thinking about functions, one important thing to think about is that for functions, each element of the domain is unique. In other words, there's only one possible value produced by the function given any particular input. One way to think about this is to imagine drawing a vertical line through any graph that you have.
So for example, you might consider asking whether, say, something that looks like this is the graph of a function, or something that looks like this is the graph of a function. And the way to test that is to ask yourself, at every single value of x, could I draw a vertical line and hit the function exactly 1 time or 0 times? On the first graph, you can see that we're fine. You'll have to imagine that my lines are truly vertical, but we're fine. There is no point along the domain of the function where I can draw a vertical line and have it hit the graph twice. On the second graph, however, you'll see that there are many places where I can draw a vertical line and hit the graph more than once. So while this first graph would be a function, this second graph would not be a function.
If you have two functions, f of u and g of x, you can create what's called a composite function, basically by substituting one function in the place of the variable input into the second function. So for example, if you have a function that you would like to create, where you would like to create a composite, you indicate it as shown here on the left, f circle g of x, which is usually read f composite g. And what you're doing is in every place in function f where there is a u, you enter the entire functional form of function g. You can create a composite in the opposite direction. It will create a completely different function. So g composite f is not the same as f composite g. Here you're creating it by every place there is an x in the function g of x, you will substitute the full functional form for the function f of u. If you're trying to think about the domain and range of a composite function, you're going to have items in the domain which successfully get processed through the entire function. So in other words, if you take an element that is in the domain of the first function, run it through that function, that produces an element that is in the range of the first function. You then take the element that's in the range of the first function as part of the domain of the second function, run it through that second function to see whether or not it's in the range of the entire composite function. This is something that really you learn to do by practice. It's a little hard to grasp right away. So we're going to do a few examples. So let's consider a few composite function examples. Let's imagine that we have a function f of v, which is equal to v squared minus 6v plus 5. And similarly, we have a function g of x, which is equal to 2 plus x. So what we'll do is if we want to take the composite function f composite g of x, that's the same as saying we're taking the function f and plugging into it the function g of x, which in this case, if we look at the function g of x is 2 plus x. So I'm going to take the function v squared and plug into it 2 plus x squared minus 6 times, now we have v again, I'll plug in 2 plus x plus 5. And if you want to, you can simplify that. Get something like 4 plus 4x plus x squared minus 12 minus 6x plus 5. You can combine your terms. You get x squared. Now I'm going to combine these two x terms. I'm going to have minus 2x, and then I'm going to combine my three integer terms. I have negative 12 plus 4 is negative 8 plus 5 is negative 3. So it's important to realize that in almost all cases, the reverse composite function is not the same thing. So now if we think about plugging in the function f of v into x for g of x was 2 plus x. So we're going to get g of f of v is equal to 2 plus v squared minus 6v plus 5, or simply v squared minus 6v plus 7. So you can see the two functions are completely unrelated with one another. So now let's add another function. H of y is equal to 1 over y plus 1. And we can do a composite of several functions in a row. We would have, say, h composite g composite f of v. And we're going to take the composite g of f of v and put it into the function h of y. And we get 1 over v squared minus 6v plus 7 plus 1, or simply 1 over v squared minus 6v plus 8.
The final functions concept for today is the concept of an inverse function. So we talk about the inverse as a function that will undo the action of the first function. So if you take a value x and you run it through function f of x, and then you run the result through function g of f of x, that will produce your original input, the value x, for every element x on the domain of function f of x. Similarly, if you do it in reverse for an inverse function, you take a value y that is in the domain of function g of y, you run it through the function g of y, and then you take the result and plug it back into the original function f of x. The result will be your number back again. It's a little hard to think about that as in abstract concepts, but you can think about it in terms of something like multiplication and division. If you have a function f of x that is equal to 5x and a function g of y, which is equal to x over 5, f of x and g of y are inverse functions of one another, because multiplying by 5 does the exact opposite of dividing by 5, and if you did one and then the other, you basically undo the action of the first function. It's worth noting that inverse functions are only inverses our inverse is in both directions. So if g of y is the inverse function of f, then f must also be the inverse function of g. So now let's consider function f of x, which is equal to 3x minus 8. And we're going to think through its inverse function. So let's think about the function g of y here, which is y plus 8 over 3. We can see that g of y is the inverse function of f of x by considering the composite function f composite g of y. And we'll go ahead and put in the function y plus 8 over 3 for the value x minus 8. And what we see when we multiply it out is that the 3's cancel one another here. We're left with y plus 8 minus 8 equals y, the number that we started off with. And you can probably see that if you did it in the opposite direction, the function g composite f of x would give you back your initial value x. So we can say that g of y is equal to the inverse function of